In this video, I want to use the divergence theorem to calculate the surface of a cube. Of course, there would be no need to do that because we already know the surface of a cube. So let me sketch a cube whose sides are all equal to, let's say, a, and therefore this means that the surface of the cube is equal to 6, which is the number of faces, times the area of its face, which is a squared. So 6a squared is the surface of this cube. Let's put our origin at this vertex. We have x, y, z, which are our axes. As I said, there would be no need to apply the divergence theorem because we already know the answer. But I think that this video would be very useful in order to understand even more deeply the divergence theorem, because it is not so obvious how to use the divergence theorem to find the answer by calculating the divergence of the normal and integrating the divergence of the normal over the volume of this cube. So let's see how to do it. And if we take a look at the cube from above, like this, we have the origin here. This is the z-axis coming out of our screen. Then here we have the y-axis, and then here we have the x-axis. What is the normal? So how can we define the normal? Well, of course, for example, here on this face, we have this normal, which is n hat. We usually call it that. Then on this other face, n hat is different because it will be perpendicular to the one that we have drawn here. Here it is like this, and here it is like this. And what about the normal inside this volume? Can we define a normal inside the volume? Well, the most logical decision here is to consider the normal to be 0 inside this volume. So we have to try to use the divergence theorem in this manner. We have integral ds, and if we want to use the divergence theorem, we have to rewrite it over a volume, not over a surface. And there is a trick to do that. We can put n dot n here times ds, because n dot n is equal to 1. The dot product between the normal with itself is equal to 1. There is nothing major about this. But now we can apply the divergence theorem because this is our function, this is our vector field f. So this is an integral of the divergence of f, which is our unit normal, dv, like this. And now you can see that it is not so easy to calculate the divergence of the normal. So the divergence of the normal would be the derivative of the x component of the normal with respect to x plus the derivative of the y component of the normal with respect to y plus the derivative of nz with respect to z. And we have to find these three derivatives. Now let's try to reason for ny, for example. So this is not ny, this is the normal, the generic normal n here, and at this surface, on the face of this surface, we'll have the components 0, 1, 0, because it goes along y. And whereas here, for example, it will be 1, 0, 0, and here it will be 0 minus 1, 0, and you get the idea, of course. Let's think about ny, the y component of the normal. We can do something similar for nx and nz. So the component ny will be equal to 1 here on the face of this cube, on this face here that I have highlighted. On each point of the face it will be equal to 1. Whereas if we move slightly inward, so inside the cube, ny will be 0. And it will be equal to minus 1 on this other face. So we can define a function like this. We can define a function over y. In particular, this is 0 and this is a. the normal ny will be equal to 1 at a, so here it will be equal to 1, and it will be equal to minus 1 at 0, here, like this, more or less. And we can assume that after a it will still be equal to 1, and before 0 it will be equal to minus 1, like this. So just slightly after a it will be still equal to 1. We can make this assumption because it will be useful to calculate the derivative. We are not really interested in what's happening here or here, because what we are interested in is between 0 and a, and also at 0 and at a. In general, we also need to extend our function slightly after a and slightly before a, because we need to take a derivative. In this case, we are interested in this one, dny over dy. So when we take the derivative in the neighborhood of the point a, we need indeed the neighborhood. So we need to know what's happening here and also here. And when I take the derivative of this step function, so this has become a step function here, I will get a delta, a Dirac delta here, like this. So maybe I can simply draw also the function dny dy, and at the point y equal to a, we will have a positive Dirac delta. It will be delta of y minus a for every x and every z. That doesn't matter. And here at at y equal to 0, we will also get a positive Dirac delta because we still have another step function here. There is a step whose, let's say, height is equal to 1 because we go from minus 1 to 0, and is equal to 1 here as well because we go from 0 to 1. And then between 0 and a, this derivative will be 0 because we defined this ny to be 0 between 0 and a here. Okay, so we have our function dny over dy. It will be the sum of these two Dirac deltas. So dny over dy will be equal to delta of y, this is delta of y, plus delta of y minus a. And something similar for the derivative of nx with respect to x, it will be delta of x plus delta of x minus a. And similarly for the derivative of nz with respect to z, it will be delta of z plus delta of z minus a. So I have already described more in detail the Dirac delta especially when I talked about Fourier transforms and also the Fourier series. It is a function which has an important property, and it is the property that we are going to use. And that property is the following. So if we integrate the Dirac delta, z minus, for example, some point z0, dz, and we integrate over a region that contains this point z0, and this is like the area under this function, quote unquote function. It is not exactly a function, but we can think of it as a function, and this is equal to 1. So the Dirac delta is not really a function because its value is equal to infinity. For example, this function here is equal to infinity when z is equal to z0, and it is equal to 0 otherwise. So we get infinity because when we take the derivative of this function ny at the point A, you can see that we have a jump. So we go from 0 directly to 1. So when we take the derivative, we get an infinity because we have 1 minus 0 divided an infinitesimal dy, if you want. So this will give me infinity. It's quite informal, but this is just to give you the idea. And now we can rewrite our integral, our divergence theorem. So we have integral ds equal to integral of n dot n ds equal to integral divergence of n dv, which is equal to integral dnx over dx plus dny over dy plus dnz over dz dv. And now we can substitute the expressions that we found here, here, and here, and we can rewrite this integral as a sum of the following three integrals. So we have an integral over the volume, and so I integrate from 0 to a, integral from 0 to a, integral from 0 to a, and I will rewrite the first one, which is the derivative of nx with respect to x. So I have delta of x minus a plus delta of x dx dy dz. So this first one I will integrate over x first, and then I have plus, let me go here, integral from 0 to a, integral from 0 to a, integral from 0 to a of delta of y minus a plus delta of y dy dx dz. So in this case I integrate over y first, plus you get the idea, integral from 0 to a, integral from 0 to a, integral from 0 to a of delta of z minus a plus delta of z. In this case I integrate over z first, dx dy. And now the integral of these two Dirac deltas will just give me 2, the integral over x here. The integral over y here will give me 2, and also this integral here will give me 2. So basically I have twice the integral from 0 to a, integral from 0 to a, dy dz, plus twice integral from 0 to a, integral from 0 to a, dx dz, plus twice integral from 0 to a, integral from 0 to a, dy dx, and this integral here is equal to a squared, this integral here is equal to a squared, and also this integral here is equal to a squared. So basically we get 6a squared, which is exactly the result that we wanted to find.